So now that we've derived the regular solution theory for describing the Gibbs energy of a concentrated mixture, in order to accurately describe the phase behavior, what we're going to want to do is we're going to want to use that regular solution theory in order to derive a model to describe the Gibbs energy or the chemical potential of the system. And so for the chemical potential for species A, it's just going to be G mix, the partial derivative of that with respect to the number of A molecules. Okay. Now, as we've seen before, we could describe that chemical potential like this. And if we take the partial derivative of our Gibbs energy model, we'll get the following. X, and I'll write out A here just to indicate what we're looking at. Okay? One thing I'll point out, just by sort of convention, we see here that we have this energy term and the standard state chemical potential. Typically what people do is they kind of combine these terms, since that energy term is not a function of the A mole fraction. Okay? All right, and so the chemical potential for species A can be described like this. And just to avoid any confusion, I'm going to add back the KBT terms here. So KBT ln of XA plus KBT chi AB 1 minus XA squared. Okay? And for the chemical potential of species B, we could write it like this. So you would just take the partial derivative with respect to NB. Okay. All right, and so using these chemical potentials, we know that at equilibrium, the chemical potentials in the different phases would be equal to one another. And so you would use this sort of expression in order to describe that. Okay. All right, so, in the regular solution model, we have this interaction parameter term. In order to kind of gain some physical intuition about it, one way you could think of it is that this interaction parameter represents energetic cost of transferring a molecule of B into a medium of A, or vice versa. Right? And so essentially what it's describing is, let's say you have a B molecule here, and originally it's in contact with another B molecule. By making the mixture, for some of the molecules, but not all, but for some, what you're doing is you're ripping it away from its former B partner, and you're putting it in contact with an A molecule to end up with this, right? And so the interaction parameter kind of describes the difference in the internal energy for those two different scenarios. Mathematically, if we remember, that sort of situation is described by this, right? So essentially we're comparing the energy associated with the AB bond, and we're subtracting off the energies associated with the AA and the BB bond. All right. Okay, and when it comes to the chemical potential of a concentrated mixture, or in general, your chemical potential for species I can be described like this. So we have our standard state chemical potential, the KBT term, and then the natural log of the mole fraction times this sort of gamma parameter, right? Where this gamma parameter is called an activity coefficient. Okay? Where gamma is going to be a function of the mole fraction of species I. All right, so depending on what your mole fraction value is, that will affect the gamma term, right? And that's essentially what we see here, right? Because this term here is essentially our natural log of gamma, all right? And we see it's a function of XA.